In this next section, we're going to talk about logarithmic differentiation. Logarithmic differentiation, unlike the name, does not necessarily mean we're taking derivatives of logarithms. Instead, we're going to use logarithms to take the derivative of more complicated functions. There's two main uses for logarithmic differentiation. The first is to simplify the process of differentiation when our function f of x involves products, quotients, or chain rules. Again, for chain rule, think general power rule. So if I've got a function that's got multiple operations in it, sometimes that logarithmic differentiation will make the derivative process simplified. An example of something like this would be, let's say I had the equation y equals the square root of x squared plus 5 over x plus 9. Okay? As we can see in here, if I wanted to take the derivative of this, it would involve a chain rule, because I've got a square root. It also has a quotient rule and some power rules in there. So I would have to use all of those different rules to take the derivative. Okay? And again, logarithms will help simplify that. The other use of logarithmic differentiation is to differentiate functions that have a specific form. And here we're looking at ones that have the form g of x to the h of x. Okay? Now notice this form is different than both our power rule and our exponential rule. So before we've had things like a to the x, where a was a constant, and we used our exponential properties. And we've also had things where x was to a numerical power, so x to the 5th or x to the 7th. In this case, we are actually talking about functions where x is both in the base and in the exponent. And these are ones we haven't dealt with up till now, but logarithmic differentiation will help us solve those. So an example of this one, probably the nicest example of this one, is just y equals x to the x. Okay? So let's look at logarithmic differentiation for both of these types of functions. So to take a derivative using logarithmic differentiation, the process is as follows. First, given either of these expressions, we're going to start by taking the natural log of both sides. Okay? And here it is important to distinguish between your bases on your logarithm. Again, we want the natural log because then we don't have to worry about using the chain rule to take the derivative. Natural log, we know, is just going to be 1 over the argument times the derivative of the argument. If I use a different base, then you've got to apply your chain rule to that other base. Okay? So we'll take the natural log of both sides. Once I take the natural log of both sides, then what I'm going to do is I'm going to use my logarithm properties to rewrite the right-hand side of the equation. At this point, if you don't remember your logarithm properties, I would pause this video and kind of refresh yourself on them. We're going to use a number of those properties for this. Once I've rewritten the side, so simplifying it out using the logarithm properties, then I want to take the derivative implicitly. So using the methods we talked about in the last section, we're going to take the derivative of the equation. And both sides are going to be implicit. One side is going to be all x's, but we'll use the natural log properties. The other side will be a natural log of y. And we'll see this in the example in just a moment. Once we've taken the derivative, of course, isolate dy dx, and simplify. Now again, with implicit differentiation, once I get my dy dx and I've simplified it, remember that my derivative can involve both x and y. But here, if you remember, we're starting with explicit functions, meaning I can write them as y equals some f of x. So for logarithmic differentiation, there's one last step, and that is to go back and replace y with whatever your f of x was. Okay? So when I look at my derivative should be entirely in terms of x. Okay? It should actually be explicit. Okay? So let's look at that first example. Y equals x squared plus 5 over x plus 9 underneath the square root. Okay? So using our logarithmic differentiation, we're going to start by taking the natural log of both sides of this equation. So if I take the natural log of y and the natural log of this square root, we can then use our log properties to rewrite this right-hand side. So ln of y, our log property says the power can come down front, so this will be 1/2 the natural log of x squared plus 5 over x plus 9. Then we can separate this to 1/2 ln x squared plus 5 minus 1/2 ln x plus 9. Okay. Now we can take our derivative implicitly. So again, on the left side, derivative of natural log of y, it's going to be 1 over y dy dx. On the right-hand side, that 1/2 is just a coefficient, so it'll get carried along. Derivative of ln of derivative of ln of x squared plus 5 is going to be 1 over x squared plus 5 times the derivative of the x squared plus 5. And same thing here. The 1/2 gets carried along, derivative of the natural log times the derivative of the inside. Okay. Again, we want to isolate dy dx and simplify. For these, simplifying just means I'm going to combine this stuff down as much as I can. So 1 over dy dx. Notice the 2's here will cancel out, so I'll have x over x squared plus 5 minus 1 over 2x plus 9. Okay. I can go ahead and combine, so get a common denominator, which is just going to give us 2x squared plus 9x, 18x, minus x squared plus 5, all over 2x squared plus 5 times x plus 9. Again, that's the 1 over y dy dx. So combining here and multiplying through by y, we'll see we get x squared plus 18x minus 5 over 2 x squared plus 5 x plus 9 times that y. So y again, we're plugging back in, x squared plus 5 over x plus 9. And there would be our derivative. Okay. And again, we notice if I can factor or simplify, we'd certainly do that. In this case, since that's as far as we can go, we'd leave it there. Okay. If you want to simplify further with the roots and cancel things out or combine your powers, you can, but this right here is a good answer. Okay. If you can get that far, then that would be full credit. Let's look at the next example. Y equals x to the x. So y equals x to the x, again, is our second type of logarithmic function, where if I look at it, I have x in both the base and in the exponent. And so here, when I do my logarithmic differentiation, I can use my exponential power properties to bring the power out of the exponent. Okay. In this case, when I do this and I go to take the derivative implicitly, notice your right-hand side is a product rule. Okay. So again, I'll have an x times an ln of x over there. On the left, my derivative is 1 over y dy dx. On the right, I can see I'll take my product rule, so 1 times the natural log of x plus x times 1 over x. Okay. From there, again, I want to isolate my dy dx, so I'm going to combine things over here. And then multiply through by y. And again, remember here, y was x to the x. So there would be my derivative for y equals x to the x. Okay. In this next example, let's look back at that first case. So here again, I've got an expression that's got some multiple properties if I were to use just basic differentiation techniques. So in this case, I can see there's a power rule, there's a quotient rule, there's some chain rules. So I'm going to use my logarithmic differentiation to rewrite the expression. So taking the natural log of both sides, we can see using our properties, excuse me, the right-hand side is going to expand to 3 natural log of 2x minus 5 minus 2 natural log of x minus 1/4 natural log x squared plus 1. Okay. So again, that's just using our properties. So again, if you don't remember how to do that, go ahead and pause that and work that out. Okay. From here, again, we'll take our derivative implicitly. So we'll get a 1 over y dy dx. And again, on this side, we'll use some chain rules on those logarithms. So we get a 3 times a 1 over 2x minus 5 times 2 from the first. Okay. So again, 1 over the argument times derivative of the argument. Here, just 2 times 1 over x. And for the last one, we'll get a 1/4 times a 1 over x squared plus 1 times a 2x. Okay. Combining things on the right-hand side, we'll get a 6 over 2x minus 5 minus a 2 over x minus x over 2x squared plus 1. Okay. And again, we can combine those. So our LCD for this is going to be 2x minus 5, x squared plus 1, multiplied by the missing pieces. So here I need a 2x and an x squared plus 1. Here I'm going to need all of the other pieces other than x. And for this last one, I need the x times the 2x minus 5. Okay. From here, we're going to combine terms. Okay. All of this is still 1 over y dy dx. So we'll get a 12x cubed plus a 12x minus, looks like 4x squared plus 4 times a 2x minus 5, which we can simplify. minus a 2x cubed plus 5x squared. Okay. Combining those middle terms, we can see if we FOIL that out. Well, let's go ahead and combine this stuff. So we get a 10x cubed plus a 12x plus 5x squared minus an 8x cubed minus 8x plus 20x squared minus plus a 20. Now lastly, we can combine those terms. So we'll have a 2x cubed. The x squared terms, we have 25 of those. The x terms, we have 4 minus plus a 20 over the 2x minus 5, x squared plus 1. And for dy dx, we need to multiply through by y, which was 2x minus 5 cubed over x squared 4th root x squared plus 1. Okay. Now again, there's some more things you could cancel out, but again, if you get this far, that's going to be full credit. Alright, let's look at one last example. Let's look at y equaling 1 plus e to the x to the natural log of x. Now again, in this case, the thing to notice is I have an x in the base and also an x in the exponent. So this is that second type of equation again. So using our logarithms, we can rewrite this so that we can get that x out of the exponent. Using our implicit differentiation, we get 1 over y dy dx equals 1 over x, so derivative of the first times the second, plus the first times the derivative of the second. So notice here, 1 over the argument times the derivative of the argument. That's where that other e to the x comes from. From there, we'll go ahead and rewrite. So here, not a whole lot we can do. This is ln of 1 plus e to the x over x plus e to the x natural log of x over 1 plus e to the x. And then from there, solve for dy dx. By multiplying by y, which again was 1 plus e to the x to the natural log of x. Again, for these, you do not have to take this further. If you get to this point, that is full credit. So there's our logarithmic differentiation. And again, for these, you're going to be seeing both types of problems in the web assign and in the written assignments and on the exam. For the second type, the biggest key is to make sure that you realize there's an x in both the base and the exponent. So for problems like this, a lot of people want to go right to that power rule or right to that exponential rule. But again, with x's in both places, you have to use the logarithmic differentiation.